First of all, I would like to say hello to everybody. I have many friends and colleagues in Moscow and in the rest of Russia, and it's my pleasure to have the possibility to speak with you today and to present us a general lecture which, as you will see, deals with many aspects of science, but especially of chemistry. So, let's start. This is your science festival, I understand, and it's a very good idea to organize these science festivals because we should bring science to the general public so that the general public can understand, know what's going on, and support science in the society. Now, the topic of my lecture is very broad, from matter to life. That's a very general topic. But the question then is, has chemistry something to do with it? And you realize that the answer is that chemistry indeed is at the basis of the change from non-living matter to living matter. So in order to understand this a bit better, let's start very early. We start with the initial explosion, the Big Bang, which has given rise to the universe. At that time, at the beginning here, there was no chemistry, of course. It was mostly energy, very high temperatures, no chemistry. Then the universe cooled down progressively during the age of physics. This was no chemistry, mostly what you might call physics. The universe continued to cool down, and at a certain time, when it was cool enough, atoms formed. You can see here atoms, and these atoms can then bind together to make molecules. And chemistry started at this point, more or less at this point here, in the evolution of the universe, and that's the age of chemistry. So molecules formed. These molecules made larger architectures, aggregates, defining separations, compartments, membranes, eventually giving rise to a cell, and then life emerged by mechanisms we don't understand for the moment, but we will certainly understand one day. So at that time about life appeared here on our planet, the planet Earth. There's probably life on other planets. There's very probably life on other planets around the systems in the universe. On the planet Earth, biology started at this point. But it didn't stop. Matter, which had become living matter, continued to evolve progressively, generating an organism which was capable of thinking. And you may know this famous sculpture here by a French sculptor, Auguste Rodin, which represents the thinker, this property of the human being, which is the highest property which we know of. Before I continue, let me point out one thing, which is very important to point out present days, because many people think that we should stop the evolution of science and all that. This is, of course, totally wrong. Because, you see, the universe has changed from energy, particles, atoms, molecules, living organisms, until thinking organisms. But it will not stop here. The universe will continue to evolve along here, further and further, and will produce other organisms, maybe of higher complexity than us. So from matter to life, we go from the beginning of the universe to what we know presently on our planet to be a thinking organism, us, the human beings. And I say again that on one hand there will be living beings, thinking beings probably, on other planets in our huge universe, and that on our planet the evolution of what we are and what nature is will not stop at the point where we are right now. We are just a point in space and in time. Now, this evolution of the universe can be characterized by two parameters. I can see others, but two main parameters: complexity and information in matter, as a function of time here. We have gone from divided matter to condensed matter, to organized matter, to living matter, thinking matter, and finally, maybe something else. We cannot imagine what that really is, but we cannot exclude that there is another stage of evolution which is even perhaps more complex than what we call thinking, which is, of course, for us, the highest expression of the evolution of the universe towards complexity. So, the evolution of matter happened, so to say, under the pressure of a parameter, complexity evolution. As matter has evolved along this line here, it became more and more complex. Then we can wonder what would be the big question to ask. What is really the big question? Maybe not the most profound one, but the biggest one for us. How does matter become complex? For trying to think about that, we have to ask the question, how did the universe go from the elementary particle to the thinking organism? Maybe there are even higher forms of complex matter which can be made, created. Science has developed, I would say, mostly to try to answer this question. What has been happening is that understanding the general laws of the universe is the mission of physics. Physics tries to understand the very general laws of the universe. Biology tries to understand the rules of life, how do living organisms function. And chemistry tries to build a bridge between the general laws and specific expressions of these laws. Of course, the laws of the universe are valid everywhere in the universe. And on our planet, it is these laws which have led to the organisms we know, living organisms on our planet. Now, how has it happened, this evolution? What is the path which led from divided matter to thinking matter? We can answer the question by one word. This word is self-organization. It does not tell us how it happened, but it tells us that this evolution towards more and more complex forms of matter is something which is happening on the basis of the laws which govern our universe by itself. One can even say that it is a cosmic imperative. In other words, that generating complex organisms is not an accident, but it is contained in the laws which make up our universe. So, there are two ways in which we have to consider self-organization right now until we will have a theory which covers both. On one hand, on the large scale of the cosmos, there is cosmic self-organization which results from gravitational forces. Cosmologists tell us that the universe was structured by gravitational forces which were acting on initial inhomogeneities after the Big Bang in density and in rates of expansion at very early times after the Big Bang. This is the origin of cosmic structure, of organization, self-organization at large scale. that is not what we are interested in today. We are interested in matter, which we know, and this self-organization results from the action of what is called electromagnetic forces. These bricks of the universe, the atoms and the molecules they build up, are generated by the action of electromagnetic forces which act on these pieces, on these atoms, on these molecules, and create combinations, random structural combinations. And these then will, by processes which lead to more and more complex entities where the objects bind together, lead to self-organization of the non-living and the living matter. We must understand that before there was life on our planet, before Darwinian evolution, which we know is the evolution which has generated living organisms, before Darwinian evolution, there was an evolution which had nothing to do with living matter, with living organisms. It's the evolution of non-living molecular matter before Darwinian evolution. And that is a purely chemical evolution, a progressive generation of more and more complex pieces of matter, which then progressively led to life. You can easily understand that you cannot jump just in one set from a particle to living organism. So progressively, complexity had to build up by generating more and more complex entities, from simple atoms to simple molecules to aggregates of molecules and so on. And this is chemistry, pure chemistry. Of course, once life existed, once organisms existed, there was a Darwinian type of evolution, but basically that also is a chemical evolution because the organisms depend on their genome, and I come back to that. So what is chemistry? As we said, mankind has created science for understanding what we are, what the universe is made of, how we can understand it, and how we can act on it. So within the general concept of all sciences, physics, chemistry, biology, geology, mathematics, and all that, chemistry is a science which deals with the structure of matter and the transformation of non-living and living matter. Especially the transformation is something very important in chemistry. Transformation means that you can generate new chemical objects from other ones. And that is something extremely attractive. You have a sort of a power over matter. If we go back in time, I would like just to have a brief historical overview, but very brief, and of course, not at all complete. About 2,500 years ago, there were philosophers in Greece who were thinking about how matter was built. And one of them, Empedocles, proposed that matter was made of 4 elements: earth, fire, air, and water. And the combination of these elements gave properties. Earth and fire was dry, fire and air was hot, air and water was humid, water and earth was cold. It's primitive, so to say, but it was a first attempt to try to understand what makes up matter. However, at the same time, another philosopher there had a much more profound idea. This was Democritus. Democritus proposed that matter was made of entities which one could not make smaller. In Greek language, this is atomos. You cannot make them smaller. You cannot put them into smaller pieces, atoms. This was very profound. And of course, we cannot say that Democritus discovered the atoms, but he had the right idea. Now let me just tell you, I do not know in this room, many of you are probably chemists, others are physicists, most of you are scientists, but for the people who are not scientists at all, you can very easily understand this, that matter is not continuous, but is particulate, it's made of particles. Take a piece of sugar, sugar you put in your coffee. Take a piece of sugar and put it into a glass of water. What happens? One says that the sugar dissolves. The sugar, the piece of sugar, disappears in the water. If sugar or water were continuous, you could not have this solubilization, this disappearance of the piece of sugar in water. The same is true for a piece of salt, kitchen salt. So you can easily understand that matter cannot be continuous just because a piece of sugar dissolves in water. A piece of salt, kitchen salt, dissolves in water. This is a sort of easy way to understand that matter cannot be and is not continuous. Now, over the years, and here we have made a big jump from minus 500 to plus 1700, big jump of 2,200 years. And people, scientists, that means people at that time, alchemists, and just, let's say, investigators, had come up with the fact that there were pieces which were these elements which one could generally understand, which one could discover, and they put them into tables like the one you see on this picture. This is a table from 1718 where you have nice symbols which represent elements like, for instance, copper or iron or lead or tin or zinc or gold and so on. And they have positioned these in a table. But this table had not really a rule of organization. It was a bit difficult to know why should it be organized this way. And this was not very satisfactory. However, in the middle of the 19th century, a great discovery and a great proposal was made. And that was made by somebody, I guess all of you must know, your countryman, Dmitri Mendeleev. In 1869, he wrote what I consider as one of the most important papers which have ever been written in science. He wrote this paper in the German journal Zeitschrift für Chemie in 1869, where he relates the properties and the atomic weights of the elements. And doing so, he proposes, as you can see here, to organize these elements in a table which had regularities coming from their properties and their atomic weight. This led to the beginning of what is called the periodic table of the elements. Mendeleev was very courageous because he even said that when an element, like there are question marks here, you may see here there are question marks, he said these question marks are simply elements we have not yet discovered. We will discover them, and of course, as you probably know, they were discovered. Nowadays, this table is this. Sorry, I forgot to mention that in addition to that, there is also a connection between chemistry and music. A good friend of Mendeleev was Alexander Borodin. All of you certainly know that Borodin was a composer. Prince Igor, symphonies, quartets, and so on. But Borodin was also a great chemist. He discovered at least two reactions. This is one reaction for the chemists in the room, they will understand that. And that's another reaction. In fact, Borodin himself considered that he was more a chemist than a composer. And composing was just an amusement on the side. Of course, for the general public, Borodin as a composer is much more known than Borodin as a chemist. Now, this is the present state of the periodic table of the elements, which are the bricks of matter. This is, I want to insist on it, the most important table ever written, and it is absolutely fantastic to see it. Why? Because this table is the full table. This table represents all the elements our universe is made of. And I insist, it is all the elements. In other words, you are sitting in a room in Moscow. If you went to the end of our universe, as far as you can, whatever the end means, you would have the same elements. Matter in any place of the universe is made of these same elements. In other words, mankind did a fantastic job figuring out what are the bricks making up everything in visible matter in our universe. I insist on visible matter because physicists tell us there's a lot of invisible matter. I'm not talking about that. But the visible matter in our universe is made of these elements, and I would say there is nothing else. Now this looks a bit dogmatic, but it is not really dogmatic. It's a consequence simply of arithmetics. What I mean by that? You know that elements are made of a nucleus, which contains protons and neutrons, and of electrons. And if you count simply 1 electron, 2 electrons, 3 electrons, 4 electrons, 1 electron, 2 electrons over here with helium, 3 electrons with lithium, 4 electrons with beryllium, 5 electrons with boron, and so on. You have an arithmetic series, and between 1 and 2 there is nothing. So this table is complete, like the series of the numbers is complete. You cannot put anything between. So please look at this, because here you see what mankind has been able to produce, a table which contains all the bricks of the whole universe. It is quite incredible that this has been done. And that is the playground of chemistry. That is what chemists play with. They take these elements, they combine them, they make combinations of various types and complexities, and that is where chemists play. Now, that is the structure of matter, what it is made of. In order to transform matter, that means to generate other combinations of elements, you have to have a general law which tells you how this happens. The general law resulted from the work of Lavoisier, where he said, nothing is lost, nothing is created, everything transforms. Meaning in present day language, that if you have a set of molecules, let's say, composed of a set of elements, atoms, they will react, they will transform each other, but the atoms will remain the same. And this is the basis of what is called the chemical reaction equation, without which you cannot do any chemistry. After that, one has to try to understand how matter is built up. After having said, all right, we now know what are the elements, but is there a connection between them? People realized that there are connections, and they began to propose different structures, what is called chemical structure formula. Around 1860s, the middle sort of the 19th century, many proposals were made. I just showed 3 of them: Wurtz in France, Kekulé in Germany, and Loschmidt in Austria. With present-day representation, the one of Loschmidt is by far the best, because if I show you just this, if carbon is the big circle, hydrogen the small circle, then let's look at ethanol, is alcohol. Here it is. Ethanol is CH3CH2OH. So the writing of Loschmidt was very close to what we do nowadays, except of course we replace the big circle by C, meaning carbon, a small circle by H, meaning hydrogen and so on. So at that stage, we had now gone from purely composition of matter to connectivity. But that is not enough. Is a molecule only a connection between atoms? Is it not something more? And in fact, it is more. It is an architecture. This was first proposed by two chemists. One was Van 't Hoff, very famous Dutch chemist. The other one, a French chemist, Lebel, who in 1874 proposed that the molecules made from elements had a shape. They introduced what we now call stereochemistry, chemistry in space. Molecules are an architecture. They are not only a composition. They are not only a connectivity. They have a shape. And this, of course, absolutely fundamental. We know that molecules are complicated shapes. I close by citing one person I must cite, simply because we speak about matter and life, Louis Pasteur, who was the first to understand and to propose an explanation for the fact that molecules could have a shape which could either be like a left hand or a right hand. And this is called chirality, because in Greek, a hand is kairos. So molecular chirality is the fact that molecules can be either like left hands or like right hands. This very quick history is, of course, very schematic and very partial, but I think it has shown you that we went from the atom to the molecule, and that's the way in which molecular chemistry then developed. Let's look at two milestones of molecular chemistry. First of all, let's have a look at, in 1828, a German chemist, Friedrich Wöhler, made urea. Urea is a molecule contained in living organisms in urine. He made urea by starting with a mineral called ammonium cyanate, which is a non-living entity, not contained in living organisms. So first of all, the first achievement was that Wöhler was able to transform this chemical called ammonium cyanate into urea. That was what we nowadays call a synthesis, producing this molecule. He also had another very important effect on thinking at that time, because people were thinking at that time that you cannot make in the laboratory a molecule contained in a living organism without the help of something magic, which was called a vital force. By making urea contained in living organisms from ammonium cyanate, which was not contained in living organisms, Wöhler showed that there is no difference in nature between molecules of non-living matter and molecules of living matter. Now, let's jump 150 years. In 1972, in the middle 1970s, this big molecule was made from its atoms: carbon, hydrogen, oxygen, nitrogen, cobalt, phosphorus. And this was one of the pinnacles, one of the most complex, at that time it was the most complicated synthesis, that means generation of complex molecules ever done. It was realized by the combined efforts of two groups of chemists. One was directed by Robert Burns Woodward at Harvard, and the other one by Albert Eschenmoser at ETH, the Polytechnical School in Zurich, in Switzerland. And I was at that time postdoctoral fellow with Woodward, and you see this red circle here, this ellipse, shows you the piece I made at that time. It's a very small piece, but it's part of the general one. It is also an indication of one thing which I try to tell scientists, in general chemists of course, but scientists, that when you are a scientist, you can contribute a stone, a small stone or a big stone, to science. And that stone is yours. This molecule, the production, making this molecule from its elements, took about 150 people, 150 researchers to make. And it took many years, of course. But you are part of it, and you are part of this big construction, which can be simply a molecule, or more generally, the huge, enormous building of what we call science. Now, this is a big molecule, a complicated molecule, and others have been made. Even more complicated ones have been made between 1970 and nowadays. Many new reactions have been discovered, many new processes, many new materials, many new molecules, with many new properties. And then we can ask the question, is there something else we should look at, we should study? Let me introduce this in the following way. Here you see a blue sphere, which is a cancer cell. And these violet bodies are called killer cells. These killer cells in your organisms, as you're sitting in this room, they run around your body, and their job is to find if some cells have been changed, have gone wrong, have become bad. This blue cell is a cancer cell. So the killer cells have to find the cancer cell and destroy it. If they make a mistake, either they kill a normal cell, a healthy cell, or they kill a cell which, or they do not kill, they do not find the cancer cell. So how do the killer cells know that this one is a cancer cell? We can also take another example. This is a white blood cell, and the blue dots is an HIV virus. When the HIV virus gets in collision with the white blood cell, it can now infect it. How does the virus do this? How does the virus, so to say, know that the other one is the target cell and now we can infect? I could have given many other examples. When you get a vaccination, you generate antibodies against a given illness. And these antibodies have to find the characteristic molecules which make that illness. So you see, when you look at these complex biological objects, something must happen between this cancer cell and the killer cell. Something must happen between the white blood cell and the blue virus and this virus, which tells them what the other is. This is a chemistry which happens between molecules, because as you realize, all these objects are made of molecules. They are defined by a membrane, and these molecules get in contact, they touch each other. And this chemistry now is a chemistry which we can call supramolecular. Why? Because it's a chemistry which deals with what happens between molecules. It's a chemistry which we can call beyond the molecule, which depends on interactions between the different molecules. That is why we have called it supramolecular. The basic properties of this supramolecular chemistry are, first of all, how do molecules recognize each other? Molecular recognition, that's the most basic feature. How do molecules recognize each other? First of all, this requires interactions for binding. Molecules have to bind together. They have to attach to one another. If they don't attach, they ignore, they don't know. So they have to have some interaction, some physical interactions. This is normal. But something else is very important. There also has to be information. A molecule cannot recognize another one if there is not an information process between the two molecules. This process can be simply described as a complementarity, a combination of two complementarities. Complementarity in geometry between the molecules and in interactions. A very simple picture has been given many years ago by Emil Fischer, another German chemist. In 1894, he was studying the way in which enzymes act on their substrates, their molecules they act on. And he proposed that they have to fit together like a Schloss und Schlüssel, like a lock and a key. represented here. Molecules fit together like a lock in blue and the key you see here in the middle. This is a very simple picture, too simple, but basically it is correct. Molecules recognize each other by fitting together in a general way by geometry, but also by interaction. Here is Emil Fischer. He got his PhD in Strasbourg in 1874, and we are very proud of that because he was one of the greatest organic chemists who ever existed. At that time, we were part of Germany. It is time of history, and Emil Fischer was a student in the laboratory of Adolf von Baeyer at that time at our university here. Now, let's have a look at what is probably the most important information system on our planet. I suppose most of you know that living organisms are defined by their genome. What is this genome? This genome is a genetic information which makes organisms, which makes a tomato different from an elephant and a bacterium different from a human being. This information is written with just 4 chemical letters. Chemists have given name to this group, that is one of those groups, a very simple chemical group. Another one, another one, another one. This is called adenine, so it is represented by the letter A. This is called guanine, G, thymine, T, cytosine, C. These letters are bound to a long sequence, to a framework, a linear chain, which carries these letters, a given sequence of letters. This sequence can be it's a very long sequence, a very long program, but written with only 4 letters. You know, probably, that 2 of such long chains can wrap around each other and generate this very famous double helix, which you see on the right, and which makes up the DNA, what is called the DNA, the nucleic acid, which carries the genome of living organisms. Now, so this is very fundamental. As we are existing here, we depend on these 4 letters, and the sequence of these letters that make us different from, as I said, the mouse or a bacterium. Now, let's see where these letters can come from. And let's only look at one, A, adenine. What is adenine? That's something chemically very simple. Adenine is a combination of 5 molecules of HCN, hydrocyanic acid. 5 of these molecules make up adenine. I can show you, just to tell you one case, here is HCN, HCN, and so on. So, combining 5 molecules of HCN makes adenine. Adenine is one of our letters of our genome. If you add some water, you can get guanine, and you do some other transformations, you get 2 other letters. HCN is contained in interstellar space. So, it is easy to understand, at least one can easily admit, that from HCN present in interstellar space, it happened that adenine was produced by simple chemical processes. So that is making the letter. Now, when you store the information, as I showed here in this chain, how can you read it? Because storing the information is not enough. You have to read it. This is also very simple. The reading is a binary system. Adenine can pair up, can make a pair with uracilthymine. They are very similar substances. And the pair is linked together by 2 interactions. This interaction and this interaction represented by 3 dots. The other pair, guanine and cytosine, interacts by 3 interactions. A set of 3 interactions. So you see that the reading of the genetic information happens by pairing up, by molecular recognition between complementary units. Adenine is complementary to thymine, and guanine is complementary to cytosine. So this is 2, 3, 2, 3. So the reading is binary, and very simply, the recognition between entities which bind by 2 points of interaction or by 3. Again, is rather trivial, but evolution often stopped when it was good enough for generating for going to the next step. And of course, 4 letters, 2 combinations is enough to store and to read. So, chemistry is not only a science of structure and information. So, it's not only a science of structure and transformation, as I said earlier. We must now add another property, which is a science of information, because molecules carry information. This is stored at the molecular level, and the processing, the reading, happens at the supramolecular level. Let's just have a look at this. If we try to understand how molecular recognition can happen, we can look at what Emil Fischer called locks and keys. This is a lock. These are 3 keys, and of course it's a red key which fits into the lock. So can we try to understand and produce in the laboratory artificial recognition systems just to try to understand what's going on? The simplest objects in 3-dimensional space are spheres, and in the periodic table of the elements, the Mendeleev table, there are series, especially alkali metal cations, which are a series of 5 balls, 5 spheres, lithium, sodium, potassium, rubidium, and cesium, which carry 1 positive charge. So that's a nice collection of objects which only differ in their ridges. 2 of them, sodium and potassium, are also very important in biological organisms, because we all in our body have a lot of sodium. That is why blood is salty, and potassium is very important also in many processes. For instance, sodium and potassium ions are very important in the transmission of the nerve influx along the nerves. When you make a gesture, then the order given by the brain propagates by having currents, ionic currents, which run around the nerves and are carried by sodium and potassium ions. Trying to understand this selection of a ball in a sphere regional balls amounts to spherical molecular recognition. So this is the simplest at the beginning, and that's the one has to start. Here again, there was a very important contribution from Russian scientists. This compound valinomycin is a natural product which was discovered in Germany by Bockmann. It was synthesized by Chemyakin in Moscow. There is now, you may know, a Chemyakin Institute, and a very important worker there was Yuri Ovchinnikov and Vladimir Ivanov and Stroop, Alexander Stroop, and they are Ovchinnikov was a good friend of mine. Ivanov is, I know him, and he's a good friend too. So these people have very importantly contributed to understanding the way in which valinomycin can bind the potassium ion, and this was a very important observation that valinomycin was a binding agent for potassium ions. Later it was shown that these valinomycins were able to transport potassium ions through membranes of mitochondria, and that was the work of Pressman in California. You see, this is also a nice image of science. Somebody discovers the molecule, other people make it and study it in Russia, Germany, Russia, and transport the mitochondria in the USA. We synthesized at that time molecules. As you can see, these type of objects are cyclic objects. So one has to have one more property, which is to have a three-dimensional object which has cavities. We synthesized, we made these molecules which contain cavities, crypts, we call them cryptans, and these crypts can be made of different sizes. This molecule has a small crypt, this has a larger crypt, and that even a larger cavity. This cavity is good for lithium, is best for lithium, this one is best for sodium, and that one is best for potassium. So that was an example of spherical recognition of very high selectivity. This is just to show you that some of those objects, let's have a look at this one here, this one on the right. This is the crystal structure, which again is inside. I just want to point out, as you will see in a moment, one thing. Molecules have also some aesthetic features that can be nice. And here is a sculpture. You see, I'll show it again. This is this crystal structure with the potassium inside. And that is a sculpture made by a Hungarian chemist. He was an inorganic chemist, but he is also an artist. Bela Vizi at the University of Veszprém on the Balaton Lake in Hungary. And he made for me this very nice sculpture, which is a cryptan outside, and inside he has this sphere. This is, in this case, the cavern. He makes a lot of other interesting sculptures. Let me show you 4 of them, and I would just like to indicate one, just to illustrate to you what one means. All these things you see are molecules, but you don't recognize them so well, except when you know what molecules there should be. Let's look at this one on the right here. You see that on the top right? What is this? This is called the scent of rose, the smell of the rose. For the chemists in the room, they probably know that the smell of the rose is a chemical compound called phenyl ethyl alcohol. And for the chemists, again, I show this up here is the phenyl, that's CH2, CH2OH. So that is exactly the molecule which gives the smell to the rose, but represented by an artist in a very nice fashion, very attractive. The other ones is too long, I can't get into it. But you can find many of those things if you go to the website and you go to internet and you find Bela Vizi. Now, applications. Of course, supramolecular chemistry has developed a lot over the years. This is now 50 years, more or less, has enormously developed. And many, many laboratories in all countries, of course, including Russia, have been studying and are working in many laboratories, in Moscow, in Kazan, where I know a lot of people, in St. Petersburg, in many other places, in Novosibirsk. But when also, so this develops well, is continuing to develop, and many people are working on it. But also ask the question, what about life applications? Just a few applications only in life sciences. Of course, without going into detail, you easily understand that drug discovery depends on molecular recognition. What is a drug? A pharmaceutical compound. It is a key for a biological look. What you want to do when you want to look for a pharmaceutical compound for a drug is to make a key for a biological look. So molecular recognition is the basic phenomenon on which depends the action of a drug. The drug has to find the target in an organism and to do something to it, to inhibit it or to activate it. So I don't want to insist on that. It's obvious that molecular recognition is basic for that. On the other hand, we have also been working, and I give you only examples from our work. There's a lot of other work around, of course. There's also interest in medical diagnostics. for gene transfer, and even for biomaterials. You will see this is something interesting for you. Medical diagnostics first, very quickly. That's another cryptate which is able to absorb light in the organic molecule around an ion of europium, which is also part of the Mendeleev table, of course, and the light absorbed here in the UV, ultraviolet region, is transferred on the europium, which emits a red light, so that it's sort of a nanobulb which has been used for medical diagnostics. And the machine has been made, which you see here, where this is used, this molecule is used as the label for medical diagnostics. This apparatus is now used in many hospitals, at least in France, and Dr. Giarmatis was very important. He developed this machine by using our compounds and attaching them to biological immunomolecules. A second important application, that's one which concerns transport, which is gene transfer. Gene transfer is a process by which you want to introduce a gene, a piece of DNA, into a cell, so that the cell will express the corresponding protein, going first to the nucleus, then giving the RNA, and then giving the protein. These processes are very complicated, but the first step is to introduce the DNA into the cell through the cell membrane. The DNA is a molecule which is highly water soluble. It cannot cross by itself the cell membrane well. So you have to find a way to introduce this into the cell. You have to find what you might call a vector which will wrap around the DNA and help it to go into the cell. This is of much importance for biotechnology when you want to make genetically modified organisms, something very important for mankind. I would like to insist on that. Genetically modified organisms are a very important evolution of what we can do, of power over matter, over life also. And I think the people who want to stop genetic modification are wrong. We have to develop it, we have to do further with it. On the other hand, they are also interesting for gene therapy, because some diseases result from a wrong protein, from some lack of a given protein, because there's a genetic defect. So you can try to take the correct gene, introduce it into a cell, and then generate the given protein, which is then a cure for that genetic disease. It has been developing quite well. Of course, a lot has still to be done, but it's a very interesting progress being made. Now, I told you something about biomaterials, supramolecular biomaterials, biomaterials which come from the supramolecular chemistry. And here, some of you recognize something. Supramolecular materials are biomaterials, and I don't want to insist on the details of it. You know what is a polymer? A polymer is what many of you carry. You have shirts, you have sweaters, which are made of artificial polymers like nylon and so on. Supramolecular polymers are another type of polymers which we have introduced in 1990. That means now 24 years ago. And they also can be used as biocompatible polymers. They have been used recently for cardiovascular implants. That is also an example of how basic research can lead to unexpected applications. We introduced the notion of supramolecular polymers in 1990. In 2013, I got an electronic message, an email, from the head of a small startup company who said that they have used supramolecular polymers to make cardiovascular implants for the surgical treatment of children which have severe congenital cardiac malformations and which require cardiac reconstruction. These compounds, these supramolecular polymers, were developed. Of course, the initial ones were modified by a company called Xentis, they made out of these cardiovascular implants. And these were introduced in people. Which people? Professor Leo Bucheria, you may know him, many of you may know him, very famous cardiac surgery in Moscow at the Bakulev Scientific Center of Cardiovascular Surgery, has on October 23rd, 2013, performed the first implantation in this young girl, Dominika. Here, you see her. You see her here 3 months after the 3 months checkup. She looks very happy, she is healthy, and she has no problem anymore. This has now been 5 successful implantations have now been performed, and all 5 work very well, are successes. So you see, again, an example of how science proceeds. We have proposed the idea of supramolecular polymers in 1990. Then it has developed enormously along the times. For instance, also special work by a Dutch chemist, Bert Weyer in Eindhoven, who has made very interesting supramolecular polymers. After that, somebody had to be convinced that supramolecular polymers are good for making biocompatible materials. And then they had to make material which should be good for cardiovascular implants. And then they had to find somebody ready to use this, Professor Bucheria. They had, of course, along the way, to find the money to do it, to have the finances, to create a small company. And you see, all this is a very complicated process. It was absolutely impossible in 1990 to see that someday these polymers will be used for saving the life of a young girl. Impossible. That is why I would say that one has absolutely to support basic research, because out of it come lots of discoveries and a lot of applications you cannot predict at the beginning. Now, let's continue. I'm almost finished, but not completely yet. I will accelerate a little. So, let's go back to the mainstream. Supramolecular chemistry led to understanding molecular recognition by pre-organizing locks for keys and keys for locks. Beyond that, we can now think of trying to make objects which will self-organize in the laboratory to try to control it. That means making systems which will spontaneously, but in a controlled fashion, generate supramolecular architectures. Let me just give you examples. First, I will use a biological example and then some laboratory ones. I've chosen a virus, the tobacco mosaic virus. It's a virus of the tobacco plant. This virus is made of 2,130 bricks, one molecule of the genome of the virus, the green thing here, and these 2,130 bricks, they get together, as you see on the left, generating a sort of a helix, a tower with a hole in it, and in the hole is the genome, the RNA of the virus. Now, this looks like magic. In other words, these pieces, they get together to generate this complicated thing. But it is not magic at all. With the present day knowledge in chemistry, you can perfectly understand what happens. It's a question of organic chemistry, structural chemistry, physical chemistry, and this gets together. The surface, you see these pieces here, these are these proteins, these bricks, they attach to each other by recognition interactions between the surface of the molecules, the succeeding molecules, the sequential molecules, and they get together automatically for reasons which are simply the result of the interactions between the pieces. Now, this again stresses the fact that these events are like programs, programmed events. The program is molecular, and the reading, the assembly of the pieces is supramolecular. The information is in the components, the molecules, and the processing happens through interactions between the pieces following a given recognition algorithm. So like in a computer program, you enter information, then the program operates, there's growth, and at the end you have the virus party. Let's have a look at just a few examples of synthetic artificial systems, and here I will be very brief, because this is also a field which has developed enormously. We will take a case where the bricks are organic molecules, and the connectors, the cementing units between these molecules, are metal ions, metal cations. So what can we do with this? We can make molecules and try to bind them together with metal ions. That's indeed possible. As you can see, this brown thing and the blue thing, these are two molecules which are held together by bricks, by metal ions. You cannot see them here. One is here, one here, one here. They're hidden behind. It's better seen on this, which is a triple helix. This is a double helix, and that's a triple helix where three strands, a blue one, a white one, and a red one, are held together by three ions. One here in yellow, another one here in yellow, and another one here in yellow. This double helix is structurally a double helix like DNA. Of course, it has nothing to do with DNA, but it just shows that you can make structures of this type, rather complicated structures, by letting the molecules self-assemble, held together by metal ions. Another example is this one, where you could say that this looks like microelectronics, but it is not microelectronics, it is chemistry. These units here are schematic representation of molecules which have positions here, one here, two of them, three positions, four positions, where you can bind a metal cation to hold these things together. If you choose, here I cannot go into detail of course, if you choose correctly these molecules and the metal ions in question, they will assemble to generate this kind of architectures where molecules of each type are held perpendicular to each other, and that each section, each crossover, there is a red dot, which is the metal ion which holds them together. This is just one example of identity of this type here, the one in the middle, this one, where you have three horizontal molecules in blue, three vertical ones in reddish, and 9 dots, which in this case are silver cations, which are represented here by these red dots. So you see, this is one example of what you can generate. Of course, many more complicated ones have been made, and many laboratories in the world work on this possibility to control the build-up of such type of architectures which result from the binding of metal ions with molecules. This is just another example which shows you that one can make rather nice objects and complicated ones. Here we have 3 red molecules, 3 linear ones, 4 planar molecules in blue, and 12 metal ions with these spheres here. You can see them, spheres. And these are 19 components which go together spontaneously, but in a very controlled fashion, and generate what you may call a nanocylinder. A cylindrical object with 3 cavities, 1, 2, 3 cavities of nanometric size. I come back to this idea of self-organization through programming, and you see that we can consider that the system we have seen is programmed. You have put information in the pieces, you have used a way to put them together, metal ions, to generate complicated entities. That is also in interest of nanoscience and nanotechnology. You know that nowadays, when we use these computers, which have such a fantastic power, they are all depending and made from objects which have been fabricated, nanofabrication, nanomanipulation. We can hope that there is hope, or maybe we should think about an alternative or a complement to this, which is to make pieces which will spontaneously, but in a controlled fashion, generate a final architecture. This means going from fabricating to self-fabrication, which is of course the ultimate fabrication. If you can generate objects containing all the information necessary to progressively build up to give the final device, that's of course ideal. We are far from it, but it is something which one can envisage. Just to show you how recently research has evolved. This will be very brief, very schematic, so not so easy to understand, but I want just to give you a feeling for how things are developing. I insisted on the fact that one can design systems in the laboratory which, based on information and programmation of molecules and supramolecular systems, can lead to self-organization. One can add another property. If we now try to make systems where selection can occur, we go a step further. Selection meaning that the self-organization we have just seen and which results from programming of the system in a way where you generate all the pieces, we may also try to build up systems where the system selects what it needs from a diversity of objects. This then makes possible the build-up of a chemistry where the constitution of the chemical object becomes dynamic, where it can dynamically associate, dissociate, recombine, and that makes possible adaptation. Because you can easily understand, I suppose, that if a chemical object can fall into pieces and then recombine, it can do so under the action of outside processes, like adding something to it, heating it, or shining light on it, and then the system can respond to this agent and adapt. This is the development presently of adaptive chemistry. This chemistry is of interest, let me just go to it, for developing new ways of finding biologically active substances, for making nanostructures for nanoelectronics which are dynamic in nature and also dynamic materials. I don't want to get into this, it will bring us much too far, but it is now, at least in our laboratory, the main line of research. How can we set up systems where the pieces, the components of the system can change under the action of external factors, agents, by rearranging the constitution. This dynamic chemistry introduces this new property, which is selection. And this selection allows adaptation, as I just indicated. Of interest is it that also that in terms of technology, it may lead, and it will, I'm sure, lead to self-healing materials, responsive materials, adaptive materials, and technologies. Something of great interest. Can one make materials which will heal and take the technologies out of this? So, we have started molecular chemistry, we go to supramolecular chemistry by design. Then we can introduce dynamics, and this is just sort of a way to show you how it evolves. We get to this constitutional dynamic chemistry, which then introduces the notion of selection and opens those adaptive evolutive chemistry. I would now like, so this is the present status, what happens in our laboratory, in many laboratories around the world. Let me just follow with some general considerations. What is chemistry? Let's come back to that and look about more general ways. The essence of chemistry is not just to discover, not just to try to find new molecules, to discover the ones in nature, but to create new molecules. Because many of the molecules which are made in the laboratories do not exist before you make them. So as I say, the book of chemistry has to be written, not just to be read. The score of chemistry has to be composed, not just to be played. That means chemistry has a creative power, like art. And this can be illustrated by, again, a sculpture by this French sculptor, Auguste Rodin, where the hand of the artist expresses a sculpture out of the stone. The stone does not contain this culture. It's the hand of the artist which makes it out of the stone. So chemistry can do the same. Chemistry out of the bricks of the universe, the elements, can produce very many combinations, creations of molecules and supramolecular entities and large architectures which do not exist before they have been made. So chemistry can be considered as being the art of matter. This has already been perceived by a very famous person, you certainly know him, Leonardo da Vinci. Leonardo da Vinci wrote a very famous, I consider it a very deep sentence, when he says, if you speak Italian, read the top. If not, the English is here. Where nature finishes to produce its own species. We are part of that, we are one of them. Man begins using natural things. What are those? That's the periodic table of the elements, the Mendeleev table, in harmony with its very nature. That means in agreement with the laws of physics. And then comes the very important conclusion, to create an infinity of species. This is characteristic of art, to create an artistic object, but it is also characteristic of chemistry. Chemistry can create an infinity of objects. Science has developed over the years since mankind existed. And in Greek mythology, you may know that there is a god, Prometheus, who conquered the fire. He stole the fire from the gods. He is carrying it. He's running away, hoping that they will not follow him to catch him. The point I want to make is that science has this fire, and we cannot give it back. Knowledge, you cannot give it back. Our path leads us from the tree of knowledge, from knowing things to the control of our own destiny. When science brings us knowledge, you cannot give it back. What we know, and now we have to make the best use of it. And we will control our own destiny by knowing more about how we function, how mankind, how the human body functions, and how life functions. Just to conclude, sort of looking at the future, in the past, you can see we connect in the terms of evolution with more primitive organisms. In present times, we connect between each other, human beings. What happens in the future? Maybe this, where we will be connecting with artificial entities. Now, this is not so much in the future. Many people around the world may have an artificial hand. They may have a new heart. They may have new bones. So, we are already on the way to changing ourselves. And it's a matter of more complicated objects being made, understanding better how to do it, and we will go along the way. Again, Homo sapiens, the thinker, and from there, where do we go? This is a lady, and as you can see, she's pulling her sweater. Something may happen here, huh? What do you imagine? What is she doing? Pulling her sweater. This comes from a Russian book, nanotechnology book, and this only illustrates that we will combine more and more the human body with other implants, in the future also modifying by controlling better the way the human body functions, modifying it with artificial organs made, for instance, by cellular ways, by deprogramming cells. I have no time to get into that, but also by combining what we are with other physical entities, physical objects. Question, but we are on the way already. Let me finish last slide with a mathematician. I have not shown yet any mathematician. David Hilbert is a German mathematician, very famous one, who is buried in the cemetery of Göttingen. As you know, a very famous place, a very famous university in Göttingen. On his tombstone here is written a sentence. So that is the tombstone of David Hilbert, and here is a sentence on the bottom. What does this sentence say? Wir müssen wissen. We must know. And wir werden wissen. We will know. This is, of course, a lot of confidence in the power of science, that science will tell us everything, will make us know what we do not know for the moment. I hope very much that many of you around this room, in this room, will contribute to this progress of science with a light hand here in the hand of Prometheus. This is a picture of science showing us the light and giving us the knowledge. Why we are here, what we are doing here, how we can control us, each other. So I wish all of you, especially the scientists in the room, that to contribute very efficiently to this progress of mankind. And I also hope that you will spread around you, if you are not scientists, the need not only for science, but for the scientific approach to life and society. Thank you for your attention, and I wish you a good meeting for the hour.
Thank you very much for this exciting lecture and for the satisfaction you gave us. I hope there are plenty of questions, and all of you, please forgive my Russian. Каждый может задать вопрос на русском, на английском, на французском, на любом другом языке. There is the first question.
Yeah. Okay.
Свет включите, пожалуйста.
Если можно, как человек, особо не разбирающийся в химии, пришел сюда, больше, что ли, если можно так сказать, религиозным вопросом. Вот супрамолекулярная химия пытается разобраться в проблеме появления жизни на планете. И, насколько я понял из лекции, основой всего называется комплементарность, то есть некое свойство комплементарности молекул, которые, словно кирпичики, образуются в все более сложные биологические структуры. Что, по-вашему, определяет само наличие у молекул такого свойства, как комплементарность? Она ведь и на субмолекулярном, и на субатомном уровне тоже должна проявляться.
So, what do you mean? What do you want?
He's not a specialist in chemistry, in supramolecular chemistry particularly, but he wanted to know, if the origin of life is a complementarity of molecules, how this complementarity was created.
This is just, first of all, let's be simple. The complementarity between molecules is not a question of creation, it's just the way it is. Plus attracts minus, shapes can fit together, and it's a property of matter. It's not the creation. What happens, of course, life is a very complicated property. We do not yet know for the moment how life has appeared. We know that chemical objects have become more and more complicated progressively. The step from non-living matter to living matter is still something which we do not understand. Personally, I am convinced it's a chemical feature, and the way in which molecules recognize each other, it's just one part of it. In chemical terms, the way molecules recognize each other is a result of fitting the interactions and fitting the shapes. And it just happens that our universe is made like that. An atom is an atom, a molecule is a molecule, and there's nothing you have just done to combine them and then they interact.
Ну, если вкратце сказать, то слышно меня, я надеюсь, да? То в принципе само комплементарность молекул, взаимодействие между молекулами определяется физическим законом общим. Закон Кулона, притяжение плюса к минусу или отталкивание одноименных зарядов. Ну а то, что форма молекул может соответствовать друг другу, то есть пространство комплементарность тоже свойство молекул. Вот. Но в принципе, я тут соглашусь, безусловно, и все согласятся, еще далеко не все понятно с тем, как из молекул образовалась хотя бы клетка. Да? Возможно, эти вопросы будут повторяться, я не думаю, что их надо им сейчас. Давайте следующий вопрошающий, ребят, вот так. Нет, девушка сначала вот молодой человек, потом вы.
Тоже как с химией, вопрос. В таблице Менделеева можно предсказать выделение некоторых элементов по количеству атомов. Вопрос при тоже, когда будут заполнены все свободные места, есть ли элементы вне таблицы Менделеева, предположительно, и что будет в дальнейшем происходить? Потому что, скажем, в Европе используют не таблицу Менделеева, а расположение элементов в своей форме. То есть российская как бы.
Okay, that's a question about the periodic table. If we have free spaces, how soon we will fill it, or what will happen when the free spaces will finish in the periodic table? The question not from chemists.
Yeah, the table is full. There are no free spaces anymore.
Таблица
At the
заполнена.
time of Mendeleev, there were still free spaces. And Mendeleev was courageous. He was convinced of the correctness of the table, of the organization, that the ones which were free spaces in 1860 or so, 69, would be found. And indeed, these elements were found. Nowadays, in the periodic table, there are no free spaces. The table is full. What happens is that at the end of the table, artificial elements are being created. Also in Russia, there is one at the end which is artificial element, Duplion from Dublin, and there's also Mendeleevium, and Einsteinium, and Americium, and so on. These artificial elements, they do not exist in nature. They are made in the large accelerators. But the table itself, the one we have seen, the natural table of the elements is full. There is no free space anymore.
Значит, что касается природных элементов, они все есть, таблица заполнена. Речь может идти только о получении искусственных, включите свет, пожалуйста, о получении искусственных элементов, которые продолжаются дальше. Вот. Что касается вопроса по поводу двух видов таблицы Менделеева, то есть масса изобретателей, которые изобретают сферическую, спиральную таблицу. Это никакой роли не играет, таблица Менделеева в том виде, как она есть. Ее можно по-разному демонстрировать, суть не меняется. Понятно. Во времена Менделеева действительно его смелость была, и в определенном смысле научная наглость, оставить пустые клетки и сказать, что там будут элементы с такими-то свойствами. И 3 из них было впоследствии скоро открыто. Пожалуйста, у вас был вопрос. Но можно свет-то не выключать, елки-палки. Да? Дайте, пожалуйста. Сейчас сломался. Сейчас.
I'm sorry, I would like to speak Russian. I know a few words, but not more. It's a nice language, but unfortunately I don't speak it.
Так. Работает.
Здравствуйте, я хотела спросить такой вопрос. У меня 2 вопроса. Первый вопрос.
Давайте поучимся, ладно?
И что было до Большого взрыва?
Good afternoon, I have 2 questions. The first one, what was before the Big Bang? Хороший вопрос.
Я хотела спросить, вот что вы думаете, ваше
What do you think about it?
Может быть, не точно.
I don't think much about it, it's not my field, but if you read cosmologists, they tell you that possibly, now look, I have to be careful, because cosmology is a field which you cannot really check. So, the present idea, at least one of the present ideas, and maybe I heard recently a cosmologist talk about, is that there are several universes in parallel. People now speak of multiverse and not universe. And before our universe, there was a universe which then contracted and exploded again. So that's in fact a permanent creation of a universe, and which then would disappear and create again and disappear. But you know, nobody is going to check that for the moment. At least there's a very little chance. So what I think about, all I can say is that physicists' present physical theory, the models which present exist in physics, and of course the recent discovery you may have heard about of the Higgs boson is a confirmation of that model, show that you can, with physical laws presently, describe the universe until a very tiny fraction of a second before the Big Bang. After the Big Bang. But the Big Bang itself is not described. It's out of the present models. So, I have no answer to your question. It's a very good question, and one has to ask it. But for the moment, we have no answer to that.
Сейчас, вкратце прокомментирую
I
ответ.
guess all cosmologists must ask themselves that question.
Все поняли? Хорошо. Ну,
Еще
можно
один
спросить?
вопрос.
Перед тем, как вы зададите вопрос, у нас есть комментарий от ведущего.
Большой комментарий. Завтра будет телеконференция с ЦЕРНом. Как раз с физиками, которые работают на Большом адронном коллайдере. Говорите, задавайте им вопрос.
Jean-Marie, we will have the teleconference tomorrow with the CERN, so the possibility for all of you to come and to listen.
Who is on the tomorrow?
Александр, кто
Who is
будет
in
там,
the
известно? Кто? Кто будет там конкретно?
Пока неизвестно.
Not yet. Нет.
Not yet, no.
Okay. Ваш второй вопрос.
Спасибо. Я хотела задать второй вопрос. Зачем ученые различают живую и неживую материю? Ведь живая материя, она состоит из тех же атомов, что неживая. В чем различие?
So the direct question is, why do scientists distinguish between living and non-living matter? They consist of the same elements. Why do you do this?
Oh, that's also a very good question. All right. Oh, because we don't understand yet how life appears. So we distinguish, you are right, I mean, you have understood exactly my nature, that in principle we are all made of the molecules which exist in non-living matter. But the combination of many molecules which interact with each other have given this combination, have given this property which is called life. I agree with you. The distinction between living and non-living matter, let's say it's a question of complexity. At some stage of complexity, life appears. Now we don't understand yet how. We will understand it. Let me just give you an example how one can maybe understand that more complexity gives properties which don't exist before. Take a single molecule of water, an isolated molecule of water. As maybe most of you know, water is HOH, a single molecule. A single molecule of water cannot freeze and cannot boil. A glass of water can freeze and can boil. What is the difference? A glass of water is made of all these same molecules of water. but they interact. In other words, an isolated molecule of water is molecular chemistry. A glass of water is supramolecular chemistry. New properties, boiling, freezing, refractive index, have appeared simply because rather than one molecule, one has now a collection of molecules which all interact. So, at each level, at least this is a first step, a very simple one, but it makes us realize that as molecules interact, properties appear which result from these interactions and which do not exist for the level below, the isolated molecule. So all I can say to answer this question is that as the complexity of, let's call it non-living matter, increases, at some stage it comes to the threshold where there is a change from non-living to living. What is the characteristic of life? The characteristic of life is autonomous growth, reproduction, and transmission of the inherited characters. Of course, you can say that when a crystal of kitchen salt forms, or a nice crystal of snow from water, this is a sort of organization where a higher structure, a higher complexity forms. And they even reproduce, so to say. Crystals are crystals and they make themselves. But they do not live because they do not grow, they have no metabolism, they have no genetic transformations and so on. But it's true that we have still to understand this. I agree that the distinction between non-living and living is a bit artificial, but it's linked to the fact that we don't understand for the moment how we can go from a non-living system to a living system. Let's look at it the other way. What is death? When an organism dies, what happens? It's still the same molecules, but it dies. It's not living anymore. So you see that the step from non-living matter to living matter, and the step from a living organism and a dead organism is the same bunch of molecules. But why did it stop living? That's still something we have to understand. Probably because of a lack of regulation between all the different parts. In fact, maybe your question could be taken also the other way. Not what happens when you go from non-living matter to living matter, but what happens when you go from a living organism to a dead organism.
Надо ли комментировать вкратце? Все более-менее понятно. Понятно, да? То есть вопрос перехода от одной молекулы к коллективу, то есть межмолекулярное взаимодействие, а вопрос перехода от живых к неживой материи или обратно. Если первое более-менее понятно, то второе вот возникает у вас вопрос. Большое спасибо. Сейчас, вот у нас есть кто записавший, раз, два, три.
Hello.
Я далек от химии, но у меня вопрос такой, как современная химия, есть ли у современной химии какая-то теория по поводу темной материи?
Do the current chemists have their own theory about the dark matter?
Yeah, I have this again coming back. You should ask that question tomorrow to the cosmologist, because there's a big problem right now. The matter we know, visible matter, is only about 4% of matter. All the rest, 96%, is dark energy and dark matter. People don't know what it is for the moment. So I would say I am for the moment just concentrating on visible matter. That's the matter we are made of. And okay, the rest we'll see what happens, what is being discovered. No answer. I have no answer.
Ну, понятно, что лучше вопрос задать завтра во время конференции с термином. Thank you. And the next question.
Hello, can you say something
Hello.
about your contribution in the molecular chemistry?
Sorry? Repeat.
Can you say some words about your contribution to supermolecular chemistry?
Yes, this would be a long story,
Будет очень долго.
but we
One
have
sentence
started-
summary.
Sorry?
One sentence summary.
Oh, one sentence summary. That's
If it's
complicated.
possible.
I fear it's not so possible. But let's say our contribution was, first of all, it went the following way. Molecular recognition was first introduced, and I proposed the name of supramolecular chemistry in 1978, and for the following reason. I cannot say it in one sentence, but let's be a little bit more explicit. The idea was the following: when a molecule binds selectively to another one, that means it is molecular recognition. Okay? In order to recognize, I indicated that the molecules have to attach to each other, to bind to each other, which means beyond the chemistry of molecules, which deals with the way in which molecules are built from atoms. There is a chemistry which deals with molecular systems where molecules interact. So, many people have contributed. We have introduced some of the notions, but especially the notion that there is a chemistry which deals with objects which are more complex than molecules and which depend on interactions between molecules. And that's the name supramolecular chemistry.
Okay, thank you. Next
We
question.
started with the cryptans. You have seen them.
Добрый вечер. Я не химик, но сдавала анализ крови на митохондрии, на энергию, на биологический возраст. Так вот, где калий в митохондрии или в плазме клетки, то есть где он там конкретно калий? Как связан калий с митохондрией?
It's a very special biological question about the position and situation and role of potassium in mitochondria. Where the potassium is exactly in mitochondria, if you know.
I don't know too much about mitochondria. I just know that they're very important, and that the energy corpuscles in the cell. I was interested in mitochondria at the beginning because of potassium transport through the membranes of mitochondria. But apart from that, I think you better read the books which tell you about.
Смотреть книги, и обычно речь идет о калиевых каналах, которые находятся в мембранах всех клеток, и не исключая мембран митохондрий. Пожалуйста, ваш вопрос.
Hello. Is it
Hello.
possible to artificially create a cellular structure, maybe a whole cell, in the laboratory today?
That's a good question. You know, I have more or less answered it already, because for the moment, maybe there are two approaches. One approach is to study the living cell and see how it works, how it functions, what are the components. The other way is to try to construct progressively things which look more and more like cells. For instance, some people have made vesicles, as they are called, artificial vesicles, like very small soap bubbles, and introduced different molecules in this vesicle so as to see how they interact, what they do when they are together. But there has been, for the moment, no artificial cell. Of course, you are right. The first step is not to make an organism like a human being, much too complicated. But life already exists at the level of a bacterium. That's the simplest bacterium. So, some people are trying to see what are the minimal features for a living system. This is now called synthetic biology, where one tries to find out what are the minimal pieces, the smallest number of pieces needed to have a unit which you can call an artificial cell. For the moment, it is not done. I am personally convinced that it will happen in the future. How many years it will take, I have no idea, but it will be done. But again, we come to the same thing as I said before. A bacterium is living, but the bacterium can also be dead. So what happens between a living bacterium and a dead one? That is one of the very interesting things. There is probably a disconnection of many regularity mechanisms, because in a cell things are very complicated. Many parts of the cell talk to each other, they all talk to each other, they interact with each other, there are reactions going on, and this is something which is probably this network of reactions and of structures. When it gets disorganized, then the entity is dead. And as long as it is organized and has, as the question you should ask about mitochondria, has the energy to sustain this organization, then it's living. What I told you, my talk has left out a very important point. Everything I talked to you about, the systems made in the laboratory, were in conditions which one calls equilibrium. Life is a non-equilibrium system. As you know, life is let's say, a very fragile system where when you disturb the system, then it doesn't work anymore. So we are living, life is on an edge. You can fall down very easily. And probably all these molecules, which before, one of the earlier questions was, why distinguish between living and non-living molecules matter? Simply because, of course, the molecules are the same, but the way they interact, the way they are connected, the networks they form, the reactions they undergo, this is still something which is a very complex network, and this is probably, I would say, most people probably think that is the characteristic of life. And when this network is destroyed, then the molecules are, so to say, dead molecules. The system doesn't work anymore. You can sort of, let's say it's a very simple comparison, but suppose you have a complicated electronic circuitry. If you take away one wire, the whole thing will stop. Very probably. Take a computer, the one I have on my desk here, a personal PC I have on my desk. If you take scissors and just break one wire, probably the whole thing will stop. Now, this is still very simple compared to life, but it is just a way to show that, okay, if you inhibit or one part, the whole thing may stop. Not necessarily so. And maybe in the future, that's something very exciting. In airplanes, for instance, one has now what they call redundant systems. So that if one computer fails, there's another one and two other ones which can take over. Maybe in the future, we can have organisms which have redundancy. So if one heart fails, you have another one. That would be good, no?
Okay, thank you. If you have Macintosh, it fails not so often as Windows.
See, this is that. I have a Windows here, it didn't fail during my talk.
Next question.
First, I'd like to say thank you for this wonderful lecture. The question is...
Thank you. Спасибо.
Do you, your research group, use some computational methods, such as molecular mechanics or any computational methods, to predict structure of new supramolecular structures. Is it possible to calculate some meaningful params of new structure? For example, is it stable structure or non-stable structure?
Yeah, good question. Yes. What does computational chemistry and modern methods of molecular modeling bring? In principle, yes. We do not use it very much, although now most of the programs which are available for computers can be easily used for chemistry, for modeling, and many the students in the lab, the co-workers, they very often model things, and it gets very meaningful information. This has developed and has become more and more powerful, and for instance, even proteins now. Professor Martin Karpus, who is the Nobel Prize winner of 2013, last year, he is part-time in our department, half in the University of Strasbourg, and he is one of those, probably he's the leader, the initiator, the pioneer in the development of molecular modeling and molecular dynamics methods. So this is possible, and it has been used, and it will help a lot, there's no doubt. And as the methods get better, as the computers get more powerful, we'll have better and better insight and can plan before having to do the experiment. But you know, at the end of the game, you have to make a molecule. If you want a drug to eat a pill, you have to have a compound. It's not enough to have a computer.
Thank you, it's clear. The next question, please.
Меня очень заинтересовало одно из направлений субмолекулярной химии, о котором вы упомянули. Это разработка лекарств для действия на фармакологические мишени. Насколько я знаю, в настоящий момент существуют такие методы, как молекулярный скрининг, которые позволяют подобрать молекулы, которые подходят для действия на мишени. Но после этого требуется ряд клинических и клинических исследований для того, чтобы подтвердить, действуют они или нет, и как вообще происходит все это в организме. Так вот, вопрос, методами молекулярной химии возможно ли будет сделать так, чтобы не требовалось клинических и клинических исследований? Как мы знаем, на них тратятся огромные деньги и страдают пациенты.
It's a very interesting question because she is particularly interested in one of your directions, which is the application of supramolecular chemistry methods for creation new drugs. And the natural question is, typically, after you have some drug candidate, you have to perform, your company or pharmaceutical giant, to perform the preclinical, clinical 1, 2, 3, 4 stages. You have to spend say $6 billion, okay? And maybe you will have a new drug. The question is it possible using the supramolecular chemistry approach to remove all these stages and just from molecule directly to the patient, to the clinical?
That would be very nice, you know? It would be very nice. But understanding molecular recognition, doing molecular modeling is a very good, a very important improvement for the design of a biologically active substance. Now, once you have a substance which is biologically, or you think is biologically active, I agree, there is a long way to go. Now, why? Because you don't want the compound to be harmful. You don't want the compound to be toxic. So we have developed one. Right now we have a compound which will enter an anti-cancer compound, which is presently going to enter into phase 2 clinic in patients for liver cancer and pancreatic cancer. Now this took us, most people do not know that I have worked on that. It's 12 years already. We started the work in 2002, and now in 2014, we arrive at a stage where perhaps we will know the efficiency of this drug, at least in phase 2. Not yet phase 3, not yet a drug on the market. And this has required, as you have correctly said, to go first to preclinical tests in animals, then to go to phase 1 to show that the compound is not toxic, then to phase 2 to see efficacy, and so on and so on. It's a long way. It is probable that as we understand more about how molecules interact with biological targets, as molecules get more specific, so as to go only to one target and not too many, we will probably be able to shorten the time it takes to go from the laboratory to the bed, to the patient. But for the moment it's very long. Sometimes, that's an important question you are raising, because one tries, maybe in some cases, too much to avoid any negative effects. Because some drugs may have a very good action for, let's say, 990 people, but maybe be toxic for 10 in 1,000. So the question then comes up, should one develop that? With the question being asked, if we know better about the interaction of molecules with organisms, maybe we can detect the 10 persons who would suffer from this drug, and therefore the 990 who would benefit from it could get it. It's a complicated situation because you don't want to harm people, you don't want to be toxic, but at some stage, trying to avoid all the risks stops all progress. In cancer research, for instance, it is very often allowed to go faster because there are, in many cases, there is no drug for the moment, or if there is any drug, it's very minimal. So in those cases, one can often go faster to try to bring the drug to the patient. There's also another case, a very recent one, the Ebola virus you have heard about. There are vaccines being prepared, drugs being made, and there are some drugs which are active, but which have not been used in all the steps, phase 1, phase 2, phase 3. But when the choice is between a risk for the person infected to die and the risk of having a harmful effect of a drug, if I were in that case, I would try the drug, of course, even if one doesn't know everything about it.
Okay, thank you. Next question, please.
Hello, my question is about the periodical table of intermediate. I would like to ask you if there is the final element in this table, and is it possible to find this element, and what will be the atomic mass of this element?
Although there's no other element. Element is full. I repeat what I said before, because, as you know, elements are defined by the atom defines the element. Okay? Now, the atoms have a nucleus with protons, and around the nucleus are electrons. There are also neutrons, but neutrons are just isotopes. They're just isotope of the element, but it's the same element. So, you have the change from one proton and one electron, that's hydrogen, 2 protons and 2 electrons, this is helium, 3 protons and 3 electrons, that's lithium, and so on and so on and so on. So, the table is full. Like, as I said, 1, 2, 3, 4, 5. The series of numbers is complete. So there is no element, there is no open space anymore. I understand your question that it's a bit frustrating in some way to say, okay, let's finish now, there's nothing else. But there is nothing else. There is no other element in our universe. Because our universe is made of protons, electrons, neutrons, particles we know, and that's it. I'm sorry, I cannot say more. I just think the table is full.
Okay, now
that is why I find it so fantastic. The fact that indeed there is something where we know it's full and we know that everything is made of it in our universe. Billions of light years away, everything.
All right, thank you. Next question, please. Hello, my name is Alex. Thank you for such a fruitful lections. And my question is related to our future evolution stage. You very often mention it in your lecture. So our organism consists a lot of cells. Cells consist a lot of molecules, protein, and etc. So I want to hear your thoughts about our future stage. We'll be able. So now we can foreign all processes in our organism, can change molecular structure, can create more sophisticated structure. So we'll be able in future to run all these processes by ourselves. So we'll be able.
That's a very good question, of course. Yes. Yeah, what we have, that's not easy. But you know, first we have to understand ourselves. It's, let's say, the easy answer is we already modify ourselves, but in a way which is technically easily understandable. For instance, if you have a heart defect, as I showed in this, Professor Bokeria implanted something, with a heart implant in this young girl who had a defect. So this young girl has now this artificial entity. Now it happens that this one then disappears because of biomaterials and so on, but that's something else. So this is the simple approach. The other approach, which is modifying ourselves in terms of our own build-up. This is coming. Let me just remind you of the work of Shimanaka. He showed, he got a Nobel Prize in Physiology and Medicine a few years ago, and he showed that what was that it was already known, of course, that when the egg develops of an organism, the cells, the initial cell becomes 2, then 4, then 8, then 16, and so on and so on. Then these cells specialize, then they organize, and one can understand, or at least define, which regions of the aggregate of cells will give a heart or different types of organs. Now, he showed that you see, as the organism develops, cells become specialized. Some become muscle cells, some become skin cells, some becomes the eyes and the heart and so on. But these cells all contain the same genetic information. And so he showed that you can deprogram, in other words, a cell which has become an adult cell contains all the information, but for instance, a skin cell is a skin cell because much of the information has been repressed, and only the information which leads to the skin cell has been kept. So he showed that one can take this differentiated cell, skin cell, to de-differentiate it, to make it again a pluripotent cell, as they are called, and out of that, make an organism. In other words, He took a skin cell of a mouse, a skin cell of a mouse, and made again a mouse out of it. Without an egg, without sperm, taking a skin cell, deprogramming it, and this skin cell contains all the information to make a full mouse. And he did it. So you see, this indicates that all our cells in our body contain all the information for making a new human being in principle. Now, we are far from that, but nevertheless, the fact that you can take a mouse, a complicated organism, take a skin cell, deprogram it, and let it reprogram is a step. Of course, it's still a skin cell, it's still a cell which knows what to do, because all the information is there. But it is a step in controlling the way in which an organism develops. And if one wants to develop this, we spoke about, for instance, let's say a heart. I have the impression that it is not too far away where one someday we will, rather than having to wait for a donor, if you have a heart problem, rather than wait for a donor of a new heart, you might be able to take a skin cell, deprogram it and reprogram it to make a heart. Would be fantastic. That is called regenerative medicine, which is just at the beginning. And frankly, I don't see why this would not be possible. It may be still some time away, but controlling the expression of genes, this is really the clue to it. Controlling gene expression to be able to repress and de-repress. That's what Shimanaka did.